Uh, it's a pleasure to start this workshop on holography, string theory, and discrete approaches. This will be lasting for this week, and we are starting this workshop with the first session. And our first speaker is M.Raclariu from Perimeter Institute, and she's going to tell us about new constraints on celestial amplitudes. Please, you'll have 15 minutes and then 10 minutes for questions and discussions. Please start.
Thank you very much for the introduction and invitation to be here. It's really a pleasure to tell you a bit about some recent work on celestial amplitudes, which is based on work in progress with Laurent Friedel. So to begin with, let me tell you a bit about the motivation behind flat space holography. So in the past decade, we learned from Andy Strominger and collaborators, as well as other people, that soft theorems in asymptotically flat spacetimes arise as conservation laws associated with asymptotic symmetries. And in particular, we know that scattering in the bulk is Poincare invariant, and this Poincare symmetry was shown to actually be enhanced to an asymptotic symmetry in gravity, which involves so-called supertranslations and superrotations. Now, the superrotations in particular, which are an enhancement of the four-dimensional Lorentz group to full Virasoro, were shown to be a consequence of the subleading soft theorems in gravity. And they were sort of served as motivation to study a potential holographic description of scattering in four-dimensional asymptotically flat spacetimes. So this dual theory is expected to be a two-dimensional theory living on cross-sections of null infinity. So such a cross-section goes under the name of the celestial sphere. And a first step in this direction was taken a couple of years ago by recasting asymptotic states of free-particle asymptotic states in terms of particular linear combinations, which instead of diagonalizing bulk translations, they diagonalize boosts. And so we have this picture that scattering in four-dimensional asymptotically flat spacetimes can be recast as some theory living on two-dimensional sphere. Now, the map between states in the bulk and states on the boundary has been worked out explicitly, both in the case of massless particles as well as massive particles. And it takes the form of particular integral transforms of free asymptotic particle states. In particular, for massless states, this map is very simple and is given by this integral transform here, which goes under the name of a Mellin transform. So here we have a bulk asymptotic state, which is on shell, and is labeled by 3 parameters. In the massless case, these are 2 angles or a point on the celestial sphere, labeled by these coordinates, z and z bar, and an energy. And the idea is that these asymptotic states, which are momentum eigenstates, get mapped into boost eigenstates by this integral transform with respect to the energy of the on-shell external particles. Now, this integral transform then allows us to define an observable, which is dual to the S matrix in the bulk, which has been known as a celestial amplitude. So the celestial amplitudes are essentially S matrices expressed in a different basis, namely in a basis of boost eigenstates. Now, here is a list, which is by no means exhaustive, of some properties these two-dimensional theories ought to obey. So the first one by construction is that they will be Lorentz covariant or covariant under global conformal symmetry in 2 dimensions. So this is SL2C. Now, a more interesting property follows from bulk momentum conservation or translation invariance, which maps on the celestial sphere to a global symmetry that relates celestial amplitudes involving operators of shifted weights. Now, another feature of the celestial theories is that they obey, in fact, a wealth of other constraints following from so-called soft symmetries. So these soft symmetries are associated with the bulk soft theorems, and they are generated by operators of negative half-integer dimensions, and they're also expected to involve generators associated to the canonical conjugates of these symmetries, which are the so-called Goldstone modes. These ideas have been studied in some recent work given here, but amongst other things, what we learned is that some of these symmetries, in particular the subleading and subleading ones, constrain the leading and subleading operator product expansion in Einstein-Yang-Mills theory. We have also learned, again from recent work here, that the soft symmetries obey a very interesting algebra. So there exists, in fact, an infinite power of negative dimension operators, which generate increasingly subleading symmetries on the celestial sphere and are associated with increasingly subleading modes in the bulk. Now, there's also been perhaps along complementary line of research. We also learned that the canonical conjugates of the soft modes are the Goldstones, which are tightly related to infrared divergences. And in particular, there's been some work where the soft-hard factorization properties of bulk S matrices have been recast as statements about celestial amplitudes. Now, there's also related work on various properties of scaling amplitudes in the bulk, both in the UV and IR, which have been recast in terms of properties of celestial amplitudes, some of which I will review in a moment. But meanwhile, let me just give you an outline of what I'm going to be talking about today. So to begin with, yes, is there a question? Okay. To begin with, I'm going to start off by reviewing some properties of celestial amplitudes, and in particular, I'm going to describe properties of 3- and 4-point scattering. I'm going to review some of the celestial symmetries, in particular, the translation symmetries, because this is what I'm going to be focusing in the rest of the talk, and the constraints associated with these. Then I'm going to review another piece of, I guess, physics, which is related to, which is supposed to play, expected to play an important role in the study of celestial amplitudes, which are the shadow and light transforms. And then I'm going to put together these two facts to revisit some ideas about celestial symmetries. And I'm going to focus on the simplest example of celestial symmetries, which involves just the Poincare algebra. And we're going to see that in addition to the standard momenta, which have a representation which enhance the Lorentz group to full Poincare, these momenta have some are related to in a different basis. They can be shown to have some shadow counterparts, which are also expected to act on the celestial sphere naturally, and then we will use these shadow momenta to actually show that one can constrain celestial amplitudes involving both shadow and light transforms. So this is where we're heading. So let me start off with the review of celestial amplitudes. So to begin with, I'm going to just focus on massless scalar scattering, which is characterized by a function of n on-shell momenta. And as I said before, it's very convenient to parameterize these massless momenta in terms of 3 variables, an energy and 2 angles, as well as a sign which tells us whether the particle in the bulk is incoming or outgoing. Then the map from a momentum space amplitude A, which is labeled by 3n variables, in the case of n-point scattering, is given by these integral transforms with respect to the external energies, as I said before. And essentially what this transformation does, again, is to recast the S matrix in a basis of boost eigenstates in the direction of these particles. Now, for 4-point scattering, the celestial amplitude it was shown to take a very simple form. So by Lorentz invariance, we know that it's going to be multiplied by a conformally covariant prefactor, as well as a function which is conformally invariant. So it's just going to be a function of the cross ratio on the celestial sphere. Now, interestingly, momentum conservation in the bulk implies that the celestial amplitudes are actually distributions, so they have to be multiplied by a delta function, which enforces that the cross ratios are real. So this is just the statement that the scattering in the bulk happens in a plane which crosses the celestial sphere on a circle. And finally, there is a leftover piece which can be thought of as just a Mellin transform with respect to the center of mass energy of the standard stripped scattering amplitude in the bulk. By stripped scattering amplitude, I mean just the scattering amplitude with the momentum conserving delta function stripped off. So to summarize, we know that 4-point scattering in the bulk is labeled by 2 Mandelstam invariants, by 2 Lorentz invariants, S and T. So S is the center of mass energy, T is the momentum transfer. The ratio of S and T, of T and S is related to the bulk scattering angle. And these 2 bulk Lorentz invariants have actually 2 counterparts on the celestial sphere. There is this beta variable, which turns out to be related to the sum of the external dimensions of the particles involved in the scattering process. And there is this cross ratio, which from the bulk point of view is just related to the scattering angle. So one can think about the celestial amplitudes as some kind of kind of logarithmic Fourier transforms with respect to the center of mass energy. Now, the symmetries manifest on the celestial sphere in a nice way. So we have the Lorentz symmetries, which act, as I said before, on the celestial sphere as SL2C, so global conformal symmetries, and these are generated by the standard Lorentz generators, so 2 copies of these SL2R generators given here. And this implies that celestial operators will organize into highest weight representations of the 2-dimensional global conformal group. So this is pretty standard and it's expected by construction. Now, as I said before, translations act more interestingly. And in the case of massless particles, one can see that the translation generator actually just acts on a celestial operator by shifting the dimension, its dimension. So this follows from the fact that from the bulk point of view, as we saw before, momenta are parametrized by a null vector up to some constant, which is the energy. And upon taking a Mellin transform of this factor of the energy, one arrives at this weight shifting operator. So in the case of, to summarize, massless momenta act on celestial operators by shifting their weights by 1. Now, the case of massive scalars, as well as massive spinning particles, has been studied by Lyons-Lanikov in these works here. And here is a formula for the massive momentum generator, which was shown to actually involve 2 pieces. So the expression looks a bit more complicated than the case of a massless particle. So it has a term which again shifts the weight by 1 up, but there is also this term which shifts the weight of the operator down by 1. And similar expressions have been derived in these works for the momenta associated with spinning massive particles. In that case, the expressions, we'll see them later, they will also involve spin shifting operators on the celestial sphere. So these formulas look quite involved, but later on we'll see that they nicely arise as solutions to certain recursion relations implied by the Poincare algebra. Okay, so now there are also the soft symmetries I hinted to before. I'm not going to discuss them much in this talk, but they are extremely interesting, and hopefully, you know, the ideas I'm going to talk about by in this talk, I'm going to just focus on the translations. But perhaps the ideas I'm going to talk about will generalize to actually understand these, better understand the generators of these of the soft symmetries, and perhaps also their canonical conjugates. So before proceeding, so I said that all of these symmetries imply actual constraints on celestial amplitudes. So before we proceed, let me just give an example of how these constraints act, what these constraints actually imply on celestial amplitudes. So let me focus on a celestial 3-point function of 2 massless and one massive scalar. Now, Lorentz symmetry implies that this 3-point function has to take this conformally covariant standard form up to some structure constant, which is generically a function of the dimensions of these particles. And then the main idea is that now we also have a relation constraint coming from momentum conservation. And in this case, as shown by Lyons-Lanikov, momentum conservation can be shown to imply that these 3-point structure constants are proportional to beta functions of this form. So these are the Euler beta functions, the ratios of Euler gamma functions, whose arguments are these 3 weights. Here, delta 1, 2 is the difference between delta 1 and delta 2. So this is quite interesting. So it's very much, it's unlike in conventional conformal field theories, where, of course, these 3-point coefficients, typically, in order to determine them, one has to invoke, for example, constraints coming from associativity of the OPE. So,
Anna, could
yes.
there also be delta function terms on the right-hand side like there are in the massless case?
Yes. So in the massive, yeah, that's a great question. Actually, I was gonna discuss. In the massive case, I guess, let's see. Yeah, it's a bit funny that well, in the massless case, I think if you consider, well, yeah, I think this is the point. If you were to consider the 3-point structures, so in principle, you could add to them some delta function, some 3-point functions which are proportional to these delta functions, like it is the case for just massless particles. I'm going to show that in a moment. But if you try to solve the associated constraint for momentum conservation for those Yeah, that's the point. But those would still have to obey P1 plus P2 plus P3 massive, acting on that particular singular term being equal to 0. And I think if you try to solve that constraint, in fact, we're going to see later, that is actually not going to be a consistent solution for those terms, because here it's very different.
Because the massive thing gives you a negative shift in delta.
Right. Yes.
Yeah.
Yes.
I see.
But that's a great question. So indeed, so I'm showing this case for massive particles because I'm going to revisit the derivation of massive momenta in a moment. But in fact, what I'm mostly going to be focusing on 2 and 3 point functions of massless particles at the end, and the constraints implied by what I'm going to define as shadow, as these momentum generators in the shadow basis. So we're going to see that these the associated, so just to kind of, the punchline will be that in a different basis, in the shadow light ray basis, these momentum generators can be worked out, and there is a simple way to just derive them, and then they can be used to actually derive the form of 3 point functions involving shadowed or light ray transforms of these external lines. So it's just that we're just going to be performing a change of basis and just study these constraints in this light ray or shadow basis. But before that, so I'm going to discuss the 2 and 3 point functions in a moment, which involve just massive particles. But it's also important to notice that celestial 4 point functions are also constrained by just Poincare symmetry. So of course, they'll also be constrained by soft, they're also expected to be constrained by soft symmetries. But again, I'm just going to be focusing on the very simplest case, which is that of Poincare constraints. And again, Lorenz-Zlotnikov has shown that for the case of 4 point massless scattering in this case, the constraint is that up to this conformally covariant prefactor, which is symmetric under exchange of any 2 external lines, and up to this delta function, which enforces reality of this cross ratio, the 4 point function has to be just a function of the cross ratio, z, and the sum of the external dimensions of the operator. So this constraint, so again, this is unlike conventional 2-dimensional conformal field theories where 4 point functions can generically depend in an arbitrary way on the external dimensions. So here we see that momentum conservation. So I haven't showed that, but you can find it in this work by, for example, Lorenz-Zlotnikov, that these 4 point functions have to be functions of the sum of the external dimensions. So in the case where the 4 point, at least one of these 4 points is a massive particle, actually these constraints are more complicated, and it's still, I think, more or less an open problem to understand that case. But this is just to illustrate.
If it's a massive particle, would you? Is it clear you'd have the delta function?
No, actually, in the massive. If you at least, in fact, I was gonna send you an email about this later. But when there is at least one external massive particle, I think this delta function wouldn't be here. That's one thing. But I think in the soft, if you try to take the dimension of the massive particle to a particular value, I think you will the 4 point function will collapse to something which will be proportional to a delta function in z minus z bar. So perhaps there is a sense in which, in a particular limit of the external dimensions, the massive particle is sort of taken to the boundary and this 4 point function becomes the same as what you'd expect as a 3 point massless particle amplitude up to some function. But yeah, and then this delta function will also arise in that process in this particular limit. But generically, for generic external dimensions, I think that for massive scattering, I don't think this delta function in z minus z bar will be there, because I mean, essentially, you can just solve for the moment. I should say that there is an explicit way of deriving these celestial 4 point functions by performing these integral transforms. So
I'm actually confused about this because let's see, in momentum space, the amplitudes depend only on S and T, right?
Yeah.
And so it depends on two real numbers.
Mm-hmm.
And so it can't be that we do a Mellon transform and then all of a sudden the scattering amplitude depends on more than two real numbers, right? It can't be a function on a bigger space. It can still only depend on two real numbers. But if we don't have that delta function there, and it seems that delta function isn't there in general, if you start to shadow or you don't have massless particles or something, that delta function goes away.
Mm-hmm.
And then Z and Z bar are independent or complex. They're two real numbers.
Mm-hmm.
So if F depends on beta, Z and Z bar, it's depending all of a sudden on three things instead of two. So there must be some, so I'm just wondering what the general statement is.
I agree with you. I've been trying to think of it. I haven't had a lot of time recently, but I think it would be very interesting. I actually don't know the answer to your question. I don't know yet, but I started computing the
Maybe
simplest.
it's somehow holomorphic.
Yeah, the thing is that, yeah, I mean, ultimately there should be an answer to just this integral one should be able to compute the 4-point celestial amplitude with one massive external leg. I mean, at the end of the day, it's going to be some kind of integral. It looks a bit complicated for some reason, but
or even if we shadow, you know, like Stieberger and Taylor did, or like Sharma did, even if we shadow one leg, that thing can still only depend on two real numbers.
No, I agree with you. I think at the end of the day, something nice is going to happen. It's not, but it's not super obvious, at least to me right now, how that, I agree with you. I think that it should still depend on two things. But I don't know. I don't know exactly what the statement is. Or when
Well, maybe it's a holomorphic function, and then it's just determined by its value on the real axis. Yeah. Okay. Anyway. Yeah.
Yeah. Anyways, that's an interesting question. Okay. So Andy sort of already hinted towards this question, but now there is a puzzle which has some lot of groups have been thinking about recently, which concerns the case of just massless scattering. So 2- and 3-point functions, celestial amplitudes of just massless particles are actually singular. And so, for example, in the 2-point case, they're related to the standard Klein-Gordon inner product in the bulk, which has this delta function singularity in Z1 minus Z2. And it's been shown in this interesting recent work that if one actually defines a different inner product in the bulk, where one, roughly speaking, replaces the complex conjugate by a shadow transform, then this new inner product will imply a new 2-point celestial amplitude, which will not be singular anymore. So in other words, it would just be proportional to the standard power law fall off expected or more familiar from two-dimensional conformal field theories. So we already see that in this process, one has to invoke the so-called shadow transform. So I'm going to review that in a moment. But before that, let me also give another example, namely that of a 3-point function. And one can consider, for example, the 3-point function of 3 gluons. So for example, one can take an amplitude of 2 negative helicity and 1 positive helicity gluons, which has been computed before in various works, and is taken, which this one has to be proportional to these delta functions in which enforce that either the right moving or the left moving variables are equal to one another. So we have these delta functions, for example, in z bar 1, 3 and z bar 2, 3. So again, these are just a consequence of the fact that momentum conservation cannot be obeyed unless one treats z and z bar as the real independent variables and sets one of the two sets to be equal to one another. Now, in this case, again, it's been pointed towards and perhaps concretely realized in some recent work by Sharma that if one there is perhaps a prescription which would allow you to turn this singular 3-point amplitude into the standard form of a conformal 3-point function by taking sort of holomorphic or anti-holomorphic shadow transforms. So this go under the name of light transforms. And so in this paper, there was a prescription that perhaps one could, that if one, for example, considered the left moving or holomorphic light transform of negative helicity gluons and the anti-holomorphic light transform of positive helicity ones, then one would arrive at the standard form of a 3-point celestial amplitude. So this is just to say that shadow and light transforms are expected to play an important role in celestial theories. And I should also say that the generator of this enhanced Virasoro symmetry in the case of gravity is actually also given by a shadow transform of subleading self-graviton in the bulk. And so these shadow transforms have popped up in various contexts. So let me just give a definition for them. So they are just particular integral transforms of operators. So they also arise in standard conformal field theory, and their role is to turn an operator, a primary of dimension h plus h bar and spin h minus h bar. So in other words, left moving weight h and right moving weight h bar into another primary of dimensions or weights 1 minus h and 1 minus h bar. Now this n is a normalization constant, and it can be fixed by requiring that s squared equals 1 for bosons and -1 for fermions, which gives a relation of this form, which has various solutions. Now, let me give another example in which these shadow transforms have been used. So Andy already sort of mentioned this, but what one can do is, for example, to relax this delta function constraint, which enforces that z is equal to z bar, by shadowing one of the external particles. So this will saturate the delta function and give rise to a celestial amplitude where one is scattering instead of four particles in a conformal primary basis, 3 particles in a conformal primary basis, and another one in this shadow basis instead. And if this problem has actually, this exact problem has been studied in this work, again, very recent work, where precisely this procedure was done to smoothen out this delta function singularity and then perform a conformal block decomposition of this 4-point function. Now, the counterparts of the shadow transforms are these holomorphic and anti-holomorphic shadow transforms, which go under the name of light transforms. So we have a very similar relation, but here what this transformation does is that it turns a primary of weights h and h bar into a primary of weights 1 minus h and h bar. So it leaves either the left or the right moving weights invariant, and it reflects the other one. So I should say that both of these transformations are actually isometries of the conformal Casimir. Now, these light transforms again have appeared in some recent work as exchanges in the conformal block decomposition of 4 massless scalars in the usual conformal primary basis. And so in this case, one can study the very simplest example of a 4-point amplitude, namely the scattering, the T-channel scattering at tree level of 4 massive scalars, which on the celestial sphere takes this form. And it was shown recently that up to an overall constant, this associated celestial amplitude is has 2 contributions. One of them is a set of discrete exchanges, which are scalars, whose dimensions differ by integers. And the other one involves spinning exchanges of imaginary spin and dimension equal to 1. So the latter can be identified as light ray transforms of the former. And it is these 2 contributions which, when summed up, give rise to this delta function in z minus z bar multiplied by this conformally invariant function. Now, again, in this recent work, it has also been shown that light ray transforms arise as are related to actually half Fourier transforms to twistor space. Now, okay, I don't have very much time left, but let me give you the gist of this work in progress. So here we're trying to understand, I should say that it's become clear that studying amplitudes, celestial amplitudes in basis of shadow or light transforms is actually important. So a natural question would be, can we recast also the symmetry generators in this new basis? And to do that, first of all, it turns out to be convenient to work with spinor helicity variables. So these are spinors in half representation of the SL2R left and SL2R right, subgroups of the Lorentz group, and introduce these conjugate spinors, W and W bar, which are canonically conjugate to them. So in particular, one can explicitly write W and W bar in this form. And this is nothing new, it's just a standard spinor helicity representation of the Lorentz algebra. So one can write the Lorentz generators I showed before in this form in terms of these Z and W variables. In particular, one can recover the representation I wrote down in terms of coordinates on the celestial sphere by actually picking Z to take this form. Now, more interestingly is to try to figure out what the momentum generators are in the spaces. And so in this formalism, which makes this SL2C symmetry manifest, it's kind of easy to write down the ansatz for a general momentum generator by just using the Poincare algebra. So these commutation relations actually imply that momenta on the celestial sphere actually have to take this particular form of a linear combination of 4 terms, where this alpha, beta, gamma, and delta are functions of H and H bar, which are essentially related to the conformal Casimirs, to the left and right conformal Casimirs. And so given this ansatz, then one can study the additional constraints of Poincare symmetry, namely that momenta have to commute with one another, and they have to square to 0 in the case of massless particles and to -1 in the case of massive ones. Now, the massless case turns out to be very simple because one can immediately notice that one can take PAB to just be a product of Z and Z bar. So this is the standard. Again, it's standard from spinor helicity representation of massless momenta. This has to be a rank 1 matrix. And again, by using this representation I gave before for Z and Z bar, one can recover the standard weight shifting expression for these massless momenta. Now, in the massive case, we revisited this problem to try to sort of rederive the formula for the massive momenta. And it turns out that this case is much more complicated.
Sorry, Anna, that formula you just wrote for the massless case says that you don't shift the dimension, right, in this basis?
Oh, no, actually, you shift the dimension because you can choose you can choose, well, z is 1z up to a factor of square root of omega, which on the celestial sphere can be chosen. One can pick the rescaling in this case. Okay. So it's actually, it does include, so this representation actually does include the weight shifting term.
Okay.
Now, in the massless case, in the massive case, one can use the same logic to actually arrive at 6 non-trivial recursion relations for these coefficients, alpha, beta, and gamma, and delta. I am not listing all of them here, but one of the simplest ones actually takes this form. Then one can show that a solution to these coupled nonlinear recursion relations actually can be found by considering some new functions, which we call alpha tilde, beta tilde, gamma tilde, and delta tilde, which are just functions of the dimensions or spins, respectively. So here the dimension is the sum of these operators h plus h bar, and the spin is the difference between h and h bar. So we have that alpha and delta up to these prefactors can only be functions of delta, and beta and gamma up to these prefactors can only be functions of the spin. And this ansatz automatically satisfies this recursion relations, and which then reduce to, well, actually, this ansatz automatically satisfies 4 of the 6 non-trivial recursion relations, and the 2 remaining ones simplify significantly. And they turn out to have at least 2 families of solutions. Now, this is interesting because the first family of solutions has been found by Lorenz-Lanikov by different methods. They were considering the conformal primary wave functions for spinning particles and finding momenta by these formulas for the momentum generators by looking at how they act on these conformal primary wave functions. Here we're just invoking the algebra and derive the associated recursion relations. And so we of course, we find their solution as a solution of these recursion relations, but we also find a new solution, which is perhaps simpler looking than what they have. And it's also nicer, as I'm going to show in a moment, in that it's symmetric under change of basis to the shadow basis. So what do I mean by this? So one can ask, okay, how do these generators look like in the shadow or light ray basis? And it turns out to be very, very easy to do by just studying the transformation properties of these spinor helicity variables under shadow and light transforms. And one finds that under shadow transforms, these z's go to w's and the z bars go to w bars. And so using these formulas, one can show that the Lorentz generators are invariant under shadows, as well as the conformal Casimirs, while these h and h bar operators get reflected. So become 1 minus h and 1 minus h bar. And interestingly, massless momenta under shadows, they become something else. So instead of z times z bar, one gets w times w bar. In particular, we see that for this choice of original basis, standard basis to begin with, one finds shadow momenta which are different, and in fact, they can be shown not to commute with the original massless momenta. For the massive case, the second set of solutions actually have this nice property that they are shadow invariant. So this is not a property obeyed by the Lorenz-Lanikov solution. Perhaps this is nicer because we know that this so-called shadow symmetry property is a property of the massive conformal primary wave functions. So it's perhaps nice to have an expression for the momenta which also has the same symmetry property. Now, similarly, under light transforms, it's only the left moving variables that transform. So we have z going to w and z bar being left unchanged. And we find similar, one can similarly find the associated momenta in the light ray basis. And now the punchline, so I'm already over time, but the idea is that now one can focus, for example, on the case of massless scattering and study the constraints involved by these shadow momenta on celestial amplitudes. And what these constraints automatically are going to give us is solutions which should involve external states, external particles which are shadows of conformal primary, of particles in a conformal primary basis. Okay, so now using the particular...
May I interrupt? You have 5 minutes, please.
Yes, okay, I'm going to wrap up.
Sorry, Anna, what was Z and W, what was the difference between Z and W on that last slide?
So Z and W are canonical conjugates, so they are, the W's are just d by dz, so they just obey the oscillator, oscillator pairs. Yeah. So, and in particular, they also have, I just wrote here the expression, essentially a particular section of CP1, which is the celestial sphere for Z, but one can write down a similar thing for W and show that, this formula is, the formula is reduced to what has appeared in the literature by doing so. And this is exactly what I'm doing on the first line here. I'm just working in a particular with a particular section, so particular representation for W and W bar, which unfolded turns into this formula. So it involves the differential operators as well as a weight shifting term of this form. And now one can ask, okay, what is the constraint implied by shadow momentum conservation on 2 and 3 point functions? So it's very analogous to the Laws-Lanikov analysis in the case of just usual momentum conservation. So one can start with a 2-point ansatz for an amplitude involving an operator and its shadow, and then ask if we can determine this constant by imposing that P plus P shadow is equal to 0. And one can show that actually this constraint with P shadow given here implies one recursion relation whose solutions are given here. Now, okay, the solutions one finds have to be proportional to these products of or ratios of gamma functions. These epsilons denote whether particles are incoming or outgoing, as I said before. The point is that one knows that if one takes both particles to be incoming or outgoing, then this thing has to vanish. Of course, C equal to 0 is a solution of these recursion relations, as well as certain trigonometric functions. So one can only determine the solutions up to constants and trigonometric functions. But nevertheless, if one specializes to the case which is known to be non-vanishing, one can see that this coefficient is nothing but the normalization of the shadow. So in particular, it can be recovered by explicit calculation of this shadow 2-point function. Similarly, one can play the same game for the 3-point functions, and I'm just showing here. I should say that these are just examples involving scalars. And again, here one finds a 3-point function of this form. So if one considers just a 3-point function involving one shadow, one can show that there is no solution to the recursion relation. The first time one finds a non-trivial solution when you have at least 2 shadows. And in that case, one solution takes this form. Now, I'm done at this point. Let me just make a couple of comments. So one of them is that one can generalize this analysis to 2 and 3-point functions involving spinning particles, and actually it works quite nicely. So one can so derive, for example, the formulas for 3-level gluon amplitudes. So one can recover them from these general formulas, and the results one gets from the recursion relations involving shadow momentum conservation actually agree from with the explicit computation up to, again, these trigonometric functions, which are quite subtle, and they perhaps correspond to a choice of contour integration when evaluating these integrals. So those are not given by these particular relations, but it would be very interesting to study the other constraints and try to figure out, what determines, for example, those contours of integration or those trigonometric functions. Now, I've only showed an example where one studies celestial amplitudes involving shadow particles, but one can play the same game with amplitudes involving light rays and study the associated constraints involving these momenta in the light ray basis. So to wrap up, we just showed that scattering the celestial amplitudes involving shadow and light ray transforms are actually constrained by the symmetries in the same basis. So it would be very interesting to understand systematically whether there is a new basis, for example, like that discussed by Sharma in the recent paper, in which all 3-point functions are non-singular. It would also be interesting to understand more generally the role of shadow and light transforms in celestial CFTs, and also understand, for example, the implications of soft constraints for amplitudes, for example, involving shadow and light transforms, and so on. So here we just took the very basic, very simplest step in trying to understand the very simplest set of symmetries, namely Poincare symmetries in these bases. So this is all I had to say. So please ask any questions. I'm sorry I'm over time.
Thank you very much, Anna, for the very nice talk. If there are any questions, please turn on your mic and ask the question. Okay,
well,
so
I just already asked a lot of questions, but
please, Anna.
Let's see, your third point, new basis in which 3-point functions are non-singular. So did Sharma was claiming to have found such a thing, or is there a question about that, or is there something?
He has a proposal for such a basis, and he showed that for the examples he considered that indeed if one considers these. So it's a proposal. I mean, I'm not sure. I mean, I reread. I was trying to also figure out. I have the same question. I'm not sure to what extent.
Whether he was completely claiming to.
Whether he was claiming that this. I mean, it's certainly a nice candidate. So his paper is a good. I think it's evidence for that such a basis exists. But for example, why not? I don't know. Why not consider linear combinations of conformal primaries and or light transforms or shadows instead? It's not clear. Yeah, it's not clear to me, for example, why this basis would involve light transforms and not shadow transforms, for example. I'm not sure if that question is answered, for example, in that work. But of course,
well, we could have, for example, announced that our basis would be states plus their shadows, and that would have worked, but it would have been too weird.
Yeah, I agree. Although the massless limit of the massive conformal primary wave function sort of suggests that.
I guess you should do that.
One should do that. So I don't know.
Yeah, but I guess there was some motivations of the relation to twistor theory and the amplitudes program.
Yeah, exactly. I think that's a nice. Yeah, it's a nice motivation for that. Oh, but ultimately, I think a way to answer that, perhaps studying conformal block understanding better these conformal block decompositions, perhaps would shed light.
Oh, sure, yeah.
On that question, yeah.
Yeah.
Okay. May I ask a couple of questions if nobody else has?
Of course.
So then maybe these questions are very naive, I was just wondering what the crossing symmetries, what are the constraints coming from the crossing symmetries on your amplitudes? Whether is it clear or obvious that, for example, your 4-point function, 4-point amplitude, readily satisfies the crossing symmetries?
So yes, these have been actually studied in various works before. So there are some celestial analogs, for example, crossing relations in the bulk, so that the amplitude should be invariant under exchanges of ST and U. So those have analogs in the celestial sphere, and at least one of those relations actually turns out to be the standard crossing symmetry relation on the celestial sphere. But I should say that there is also this funny thing that
exactly that. And my question was related to Andy's and regarding this delta, whether it's related to this, I mean, the crossing symmetry.
This delta, well, this delta is needed to, when you, for example, send Z to 1 over Z, you have to have the, like, everything has to.
Yeah, but we know that crossing symmetry should work for massive or massless alike, right?
Oh, you mean when you have, I don't think there has been much work on celestial amplitude, on the properties of celestial amplitudes involving external massive particles. So that's a great question. I think one should figure that out.
So maybe there's something like the holomorphicity that Andy suggested is coming from crossing symmetry. That was what I was wondering.
I see. Okay, that's interesting. Yeah, perhaps trying to understand. Yeah, there must be some fundamental, some symmetry properties like crossing symmetry, which should constrain somehow forms of all 4-point functions involving both massive and massless particles. But I don't think it has been, it hasn't been, as far as I know, at least, it hasn't been worked out.
There was a nice paper in the last few weeks by Cheng, Huang, and Li.
Ah, I saw, yes, that's right.
And yeah, they study it's related to what happens when you take the 4th point on the circle and you jump it over.
Yeah, that's right. Yeah, that's interesting. But I thought that they only had massless scattering there.
They only had massless, yeah.
I see.
But they said some new things, I think.
Yeah, they had some, yeah, I read that a while ago, so I don't. They had some statements about the optical theorem, I guess.
If I may, another question. There's this famous result due to Weinberg that spins higher than 2 lead to non-unitary interactions at massless higher spins. So I was wondering whether this has any bearing or appearance in your type of analysis. The spins higher than 2.
Yeah, so it was found by this group here that actually, upon shadowing one of the external legs, the resulting amplitude, if you were to perform a conformal block decomposition, it involves all sorts of exchanges of higher spins. In fact, this was observed earlier by Volovich, Zlanikov, collaborators and collaborators. Now, again, in this conformal block decomposition here, we're seeing, so this, I should have said that this was done in Lorentzian signature. So instead of this tower of higher spins, we have these imaginary spin operators. So this light ray operators being exchanged. But the Euclidean version of that is this infinite tower of exchanges of higher spin. But okay, I'm not sure to what extent I understand that.
Okay.
But they are present.
Basically, you're saying that we need to have all of these higher spins, and you cannot cut this spin to have some higher value. And we need to have the whole tower.
They seem to be, yes, they seem to be implied, but they seem to appear as exchanges in a conformal block. Yeah.
Mm-hmm. Mm-hmm. Okay, thank you. If there are no further questions, let's thank the speaker again. Thank you, and I thank you on behalf of everybody there in the audience. And maybe we should now move to the next speaker.